Okay, so the first thing to recognize is that we are looking at the f prime graph. This is not the shape of the original graph. This is the f prime graph. I like to start labeling what I'm exactly looking at. Right now, I'm concerned about what portion of the graph sits above the x-axis, what part of the graph sits on the x-axis, and what sits below. Right now, I'm not so concerned about whether the graph is moving up or down. Okay, we'll deal with that later. Right now, I'm just concerned about where these points are located, above, on, or below the x-axis. Okay, so the first thing I'd like to do is just go ahead and build that slope sine line. That slope sine line is going to give you a picture of the original graph. Okay, because looking at this is confusing. You don't know exactly what the graph's going to look like, but once you have that slope sine line in front of you, the rise and fall, the arrows are going to help guide how the graph's going to look. Okay. The graph starts and ends from -5 to 5. What do we place onto our sine line? What points? X-intercepts, right? X-intercept. We want to target slope zeros, meaning x-intercepts. Okay, so -3, -1, and 3. All right, good so far? Okay, so now we want to look, where is the graph located, right? So these are going to help guide you. Between -5 and -3, we see the graph is clearly above the x-axis. Look at where it's located. It's located above the x-axis. We have a specific notation for that. That's going to be a positive slope. Don't look at the fact that it's moving up or down. That's for later. Okay, we'll deal with that when we get to our concavity sine line. Okay, between -3 and -1, above or below? Above, so still a positive slope. Between -1 and 3, below, corresponds with negative slope. Between 3 and 5, above, Andrew, we're in our packet, page 19. So from here, we should be able to answer A, B, and C. Right? Let's practice doing that. Sorry, A, B, C, and D. Let's practice doing that and also writing out our because statements. I'm going to ask you on the test to write out because statements for all of these, for relative min, for relative max, increasing, decreasing. Let's practice doing that. Now for relative min and relative max, all you can do is provide the x values. Okay, we don't know the y values yet. That's okay. Just the x values for the relative min and relative max. So you should find A through D to be easy because you've done the hard part already. You've gathered everything from the sine line. If your sine line's correct, you're just converting those symbols into interval notation and because statements. Okay, relative min, 3, because f prime changes from negative to positive. Again, I want to highlight this here because a lot of students leave these out. But I'm going to specify on the test right because statements for A through D. Relative max at x equals -1 because f prime changes from positive to negative. -3 is a critical point, but it's neither, right? There's no change in sign. It'll rise. The graph will rise. It'll level off for a moment because we know there's a slope 0 at -3, but it's going to continue rising, right? So it's neither a relative max nor a relative min. Increase and decrease, we just make sure that we separate each of our intervals there. So have 3 up arrows. So I want 3 separate intervals. You can potentially sometimes get away with merging intervals together, but I would just say as a rule of thumb, just keep it safe, right? If you always separate your intervals, you're never going to run into trouble. So I like to I don't like to merge my intervals, right? Because statement, because f prime is greater than 0. Function is decreasing. We have 1 interval of decreasing, -1 to 3, because f prime is less than 0. Okay, careful with these. Most students get these right, but these two give students the most trouble, leaving those out. Okay, are we okay with the slope sine line? Okay, so now moving to part B. I'm sorry, not part D, but yeah, we're gonna now E through G, we're going to create our second derivative sine line. Okay, so second derivative sine line. Now we're going to target the peaks and valleys. Okay, so wherever there's a relative max or relative min of the f prime graph, those will be locations where your maximum steepness of your curve, of your original curve, is going to be, and we call that the point of inflection. Okay, so second derivative sine line. So -3, -2, 1, and 4. Okay, are we good there? All right, so we want to put our points of inflection on the second derivative sine line. This is not what points of inflection look like on the original graph, but this is what points of inflection of the original graph looks like if we're looking at the f prime graph. So now we look at the slope. The slope of the f prime graph is going to indicate to us what the original graph, whether the original graph will exhibit concave up or concave down. Don't look at the curvature. We don't want to say concave up, concave down. This is not the original graph, okay? So we define, this is concave down here, a negative slope is going to reflect concave down because concave down is defined as a slope becoming more negative, okay? This is all positive, but it is moving in a negative direction. That's enough for the graph to exhibit this concave down shape. Okay. Positive slope on the f prime graph is going to correlate with concave up. Negative slope corresponds with concave down. Positive slope, concave up. The negative slope, concave down. Everybody okay so far? Okay, so see if you can fill out E through G, and then because statements for each of them. Because statement for point of inflection, because statement for interval concave up, because statement for interval concave down. All right, make sure you include because statements for POI. If you can create your sine lines, writing out those statements should be the easy part, right? You're just pulling those information directly from your sine line. Any questions so far? Pretty good. Yeah.
So we're writing like the point of inflection or the relative maximum.
Yep, just the x values. Just the x values. Now, you're going to see for part H, there's going to be some information given in terms of specific points. We'll create that with our graph, and also the range is going to help us maybe identify some of those max and mins. But when you're listing them out, I'm only going to ask you for the x values. But when you graph it, we may be able to get some more clarity there. But yeah, I was just asking for the x values for points of inflection and relative max, relative min. Okay, are we good so far? Everything up to G, are we good? Sketching the graph. Okay, so this, let's spend some time on this because something that we haven't seen is this information about the range. Okay. Okay, so when I sketch the graph, I'm only going to rely on what they give us in terms of order pair and range, and then your slope and concavity sine line. Don't look at your graph anymore. This is just going to confuse you. Okay, don't look at your f prime graph. It's not going to help us at all. We're just going to rely on this and or some order pairs. Okay, so for H, we're going to create our gather some information here. So we have some order pairs, -5, -4, and we have 5, 3. Actually, it's just giving us the endpoints. Okay, so everything in between, we're either going to have to create on our own, or that range is going to help us out. -5, -4. And 5, 3. Oops, sorry. Okay. Now, what the range is telling us is that when we sketch our graph, when the dust settles, we want the highest y value to be 5, and we want the lowest y value to be -7. Okay, so we'll just go ahead and sketch our graph, and then if we need to kind of adjust and pull the graph so that it fits that range, then we'll do that. Okay, so maybe right now we won't worry about the range so much, but at the end, If we see that our sketch doesn't quite reach that interval, then we have to kind of stretch it so that it fits. Okay. So we'll put a star next to this. We have to kind of come back and kind of adjust our graph if we need to. Okay. But now let's just go to our first draft of our graph, right? We don't want to try to do too much at one time. Let's just sketch the graph. Again, you're just relying on this here. Okay. So I'll use pencil here as a way of kind of giving myself a draft here. So I know that I'm going to be rising until some point at -3. I don't know where that -3 is, but I know it's going to be somewhere in between. So -3, maybe I'll target a point that is kind of along my path. I'm expecting what at -1? The relative what? The max, right? So I want a point maybe a little bit higher than the others. And I'm expecting a relative min at 3. So I'm just kind of giving myself some targets. Okay, and your graph could be anywhere for now, because all we're doing is we're just trying to get some shape of this to show up, right? So I know I want my graph to be rising. It's going to be flattening out. Rise again to a max. Fall to some y value at 3, and then rise again until I get to 5. It's not perfect, but at least I have something to work off of, right? I know I have a general shape to build off of. Okay, so maybe my graph is not as easy to see. I'm going to make it a little more bold, but I know this is just a draft. I'm just looking at my draft. I'm looking at my slope sine line here. I'm not looking at my f prime graph. So the rest of it is just curvature, okay? But the basics are down. Now, let's go to look at that range here. What is this? How is this going to help us kind of shape our graph a little bit? What is this telling us that we should do? What do we want this point to be? We want it to be -7, right? So either I'm going to kind of rearrange this, or I'm going to pull this a little bit lower. 1, 2, 3, 4, 5, 6, 7. So after you make your draft, just make sure, are your lowest and highest points kind of fitting into what they've described as the range? If it isn't, then, well, I'll just go back and kind of make it that way. I want my highest y value to be 5, so 1, 2, 3. Okay, so I'm kind of in that range, so I'm just going to kind of define it as 5. Okay, are you guys okay with that? Just taking that graph and then maybe stretching it or pushing it in so that it kind of fits into that range that's established. Okay, next step, now we're going to go and update our graph with our second derivative sine line. Plot your points of inflection along the path of the graph. The order pair is not that important. Just wherever it lands at -3, just highlight that point. -2. 1. 4. So between each of those highlighted points, I want to kind of force a change in curvature, make it a little bit more exaggerated so I can kind of see it. Okay, so I'm starting with concave down, moving to concave up, concave down, concave up, concave down. Now, when you do concave down here, make sure that you don't do the full concave down, because we're maintaining our positive slope, right? So that's what I'm expecting from your f of x graph. Are you guys comfortable with all those steps? Okay. Last part, let's create our second derivative graph. Now, when you create your second derivative graph, you're only looking at your second derivative sine line. This is the only thing you need to look at, okay? Don't look at the graph either, just the f double prime sine line. Okay, so we're going to go ahead and plot our, I'm going to label my second derivative sine line. Above is concave up, below is concave down. Anything on the x-axis is my POI. Okay, so we have to remember that our y-axis no longer represents position. It doesn't represent slope. It represents concavity. So anything above represents where my original graph is going to be experiencing concave up. Anything on the x-axis is where my original graph is going to be experiencing point of inflection. And then below is where my graph is going to be experiencing concave down. Okay. You take your points of inflection and you plot them onto your x-axis. Right. We want our graph to live based off of our labeling here. So between -5 and -3, we want the graph to live below, but it's got to connect to this point. So between -3 and -2 is sitting above, but has to loop back down. Between -2 and 1 is below, loops back up. Right. Between 1 and 4, above. And between 4 and 5, below. Okay, you'll see virtually this exact same problem, just with a different starting graph. Are you guys okay with that? Okay. Okay, let's go to our test review. And let's do an optimization problem. Page 2, number 8. Okay, let's read this problem here. A manufacturer wants to design an open top box having a square base and a surface area of 80 square inches. What dimensions will provide a box with maximum volume? Okay, so open top box with a square base. So that square base, I know I want it to be, the length and width will be the same value, so I'll call both of these x's. But we don't know what the height is, right? It doesn't say that it's a cube, so that height is we know it's going to be a different value than the length of the either sides of the base. It says, what dimensions will provide a box with maximum volume? So we know that we see the word maximum. We know that we're optimizing volume. We know that ultimately we're going to find the derivative for volume. Okay, but first, let's build our volume. What's the volume of this box? Length times width times height, right? So okay. We would like to find the derivative for volume, but what's getting in the way here? Too many variables, right? So we have to get it down to one variable. So we need a supporting equation. The supporting equation is going to come from this other information here, surface area. Okay. So let's build our surface area equation because we know that's going to be the equation that's going to help us get to a point so that we can find the derivative. Okay, so surface area, that's exactly the formula is exactly what the name describes that. So we're going to find the area of each of the surfaces, right? Area of each of the surfaces. Okay, how many surfaces are we going to be needing to worry about? Okay, there's 6 sides, but what? Good, open top. So we're not going to have no material at the top. If it says closed box, then we would need to worry about 6 surfaces, 6 sides. Okay, but it's only 5 sides. Okay, so let's just do the bottom first, x squared. Okay, what's the area of one of the vertical faces? XH. Are they all going to be the same? Yes, so I have XH plus XH plus XH plus XH. I can merge that together to be 4XH, right? So 1, 2, 3, 4, 5. I have areas of each of the 5 sides. Okay. All right, what do you know about, what do we know about surface area here? It's 80. Okay, so there's our supporting equation. Okay. We want the h to disappear, so let's solve for h, and then we're going to slowly kind of insert it into our volume equation. Okay. Get that h by itself. Subtract the x squared first, and then I'm going to move over the 4x. Okay, so all this is now going to get inserted into the h. We're making progress because we're going to get that volume equation purely in terms of one variable on the right side. And then we can now think about what to do to get it ready for power roll. Okay, any questions so far? Okay, so now our attention is purely just with this volume equation. We just are going to try to get to the derivative or get it cleaned up so that we can get it ready for power rule. Once we get it for power rule, we find the derivative. Once you find the derivative, set equals 0, solve for x. And then you're basically done with your problem. You just have to figure out where to insert that x to answer what the problem is asking for you to find. Okay, I'm going to distribute the x squared through first. I would prefer not to do quotient rule, and the problems that you see, you should just be able to get it to power rule every time. Okay, we shouldn't have to worry about any messy quotient chain, but it does require you to take the steps to clean up, right? We got to be able to do our cleanup so that we can do power rule appropriately. So I want to try to get rid of this denominator. I know that I can split this into two fractions, right? I don't want to start canceling things out. Right, there's that minus sign separating, but let's split up into individual fractions. And we have a much easier time kind of figuring out how to get these denominators resolved. Okay, are we good with that? Okay, so now we have basically individual terms. We can clean up, move our denominators around. So 80 divided by 4 is 20. I can take one of the x's away. So the first term just cleans up to be a nice just 20x. What about the second term? What can I do there? And what's that going to leave us with? Good. So initially you may be thinking of it as x cubed over 4. Which is fine, but visually, I think it helps if you can pull that 4 out in front so it's not sitting below the x. Makes it a little bit cleaner. It makes it look more similar to other power rule problems if you have a coefficient in front rather than below the variable. Okay. So we should be staring at this thinking that, okay, this is a nice and easy power rule problem, right? But we need to get to this point. That's what I want to make sure that we can do. Okay, so no derivative yet, right? All we're doing is we just clean it up. So now we can find v prime. $20x becomes 20. Bring that 3 down. Subtract 1 from the exponent. Once you have your derivative, you're going to set your derivative equal to 0 every time. Okay, dividing by 3/4, the same thing as multiplying by its reciprocal. Not going to be a nice whole number, but I get x squared equals 80 over 3. We'll use our calculator to find some approximated value. Once you solve for x, make sure you don't just stop there, that you go back and read the problem and figure out, are you providing everything that the problem is asking for you to find? Okay, so what do we need to find? H, right? It's asking for dimensions. We have x, so we need to find h. We go searching for an h formula, which we do have, right? We built that so that we can get it ready for a volume equation. So we can find h there. Okay, rounded 3 decimal places. We have the dimensions. We have x, we have h. We have the length, we have the width, we have the height. Anything else? we also need to find what? Maximum volume. So how can we get there? Do we have some options here? Good. So actually, I do want to say something here, though, that any of the volume equations work, right? You just pick whichever one you want to use, and they will all lead you to the same answer. What you don't want to do is you don't want to do V prime. Okay, that's going to give you something else. We don't want to use V prime. If you do V prime, you're going to get 0, right? And we've already established that x is coming from the derivative. So any of the V equations you're welcome to use, even the original one, because you have h, that's fine as well. Okay. In fact, maybe this is the easiest now that you have your h. Questions there? Okay, let's do another optimization problem. If you go to page 4, last page, and by the way, this one, if you're practicing problems, omit this one. This is too much here, so don't worry. Don't worry. If you're doing extra problems, don't do this one. Let's do number 3. This is on the last page. There's a landscape architect wishes to enclose a rectangular garden. Okay, so a rectangular garden with brick wall on one side. There's cost involved. But anytime you see cost, if it's two-dimensional, you know cost is going to be kind of related to perimeter. Okay, so there's my brick side. There's my more expensive side here. The other 3 sides are metal fence, a little bit cheaper, $10 per square foot, or $10 per foot. We have area and perimeter involved. I'm just going to go ahead and label my sides. Okay, first thing to make sure, well, after you draw your diagram, is what are we trying to optimize? We need to have some anchor here. What's our goal here? Good. Minimize cost, and cost is related to perimeter. Okay, so we know that that's important, right? We want to know what equation we're trying to find the derivative for, so that we can have an idea of what to move towards, right? Otherwise, we don't know what to do with the area and the cost and the perimeter equation. But this is an important first step. We want to at least have an idea what our goal is. Okay, I'll put a star next to cost. You know, cost is very much related to the perimeter. We're basically going to add up all the sides, but then as we add up the sides, we're going to include the cost of each of the sides. Okay, let's build our cost equation first, and then we can decide what we need help with. Okay, what's our cost equation? What do you guys see? Okay, let me start you off. 10x plus Okay, right. So we're just adding up all the sides, but then we're involving the cost that associates with each side. Okay, so 10x plus 30x, that's 40x plus 20y. Okay, you guys okay with that cost equation? Okay. Okay, we want to find the derivative for this equation, but what's getting in the way here? Too many variables, right? Too many variables. So we need help. The help is going to come from the fact that we have an area, we have information about area. Okay, what's the area of this rectangular garden? XY. Replace A with 1,000. Doesn't matter which variable you solve for, but if they look the same difficulty-wise, I'm just always going to try to get my y's to disappear. Once that substitution occurs, we can move towards getting it ready for power rule. Sorry, 1,000, not 100. So I'm doing a couple of things here at the same time. I'm multiplying 20 by 1,000, but I'm also forcing that x up to the top so that I can have a nice clean power rule so that I don't have to rely on quotient rule. Okay, now that everything is ready, I can find the derivative, right? Every time with your optimization problem, once you get your equation nice and cleaned up, find the derivative, set equal to 0. Once I have my x value, I'm going back and reading the problem. It's asking for the dimensions of the garden, so I just have to find y. So there's the y formula, 1,000 divided by 22.361. Okay, you guys have the key. I encourage you guys to work through the rest of the review worksheet. I also have a morning review on my website. I also have some additional worksheets that I've worked through from the test review session, the help sessions, and I included the link of the worksheets next to those videos. Okay. Test tomorrow, morning review, 7:15 in the morning if you want to join. I'll also send a Teams link and I'll record it as well.